to the chapter where we learned how to sketch graphs. In chapter before this, we learned about main characteristics of graphs and transformations that we can apply to them. Right here, you can see how we transform trigonometric function. We compress it in horizontal direction. You see the red one is more like a compressed string to the middle. We also stretched it in y-axis. You can see the maximum and minimum value of the red function is higher than for the blue one. These all are examples of transformations to the basic function that we could do. And basically, using this strategy of analyzing transformations, you can sketch any graph knowing how is the standard function looks like. For example, cosine x is a standard function that you should know how it looks like, exactly like this blue curve. And by translating points of that blue curve, you can create the transform function, which is the red one. You see here we have a coefficient of 2 and 3 for x, 2 for the function. And that's what I want you guys to review from the previous class in order to keep up with us. Remember these transformations. You can find them right here. So in this unit, we covered turning points, and in the unit before that, this one, we covered properties and characteristics of functions and how to identify them. You see here all the definitions of intervals of increase and decrease, odd functions, even functions, continuous functions, discontinuities in functions. This is what we covered in the last class. We also covered one important formula. You should have learned it at grade 11. This formula gives you the general form for writing down a function. Let me find it real quick. Here it is. This is a general equation for function. And each coefficient in this function plays its role when identifying transformations that are applied to functions. For example, D and C are responsible for translations, and K and A are responsible for compressions and stretches in our function. You can also review that from previous class. So moving on to next chapter of our first unit, we're going to look into inverse relations. Basically, inverse should already tell you something about this function. Inverse means that something opposite to what we already get. Please take a moment to read what you're seeing on the screen. I'll get back to you in a minute. Okay, guys, did you look through? So, in to begin with, we're going to investigate what is an inverse relation on an example that are given below. Basically, the goal of today's class is to determine the equation of an inverse relation and the conditions for an inverse relation to be a function, right? We should remember that not all relation is a function, and we're going to look into it today. For example, a curve that's going to look like this may not be a function, or the curve that looks something like this is also not a function. And we're going to look into how can we identify that with exact criteria. So learning about the math. The owners of candy company are creating a spherical container to hold their small chocolates. They're trying to decide what size to make the sphere and how much volume the sphere will hold based on its radius. The volume of a sphere is given by the relationship. This is widely known formula for volume of a sphere, three-dimensional sphere. And how can you use this relationship to find the radius of any sphere for a given volume? So say, how can you express relationship between the radius and the volume when volume is the given number? Because right now, volume is something that is defined by the radius, right? Radius is independent variable here. Use a table of values and graphical model to represent the relationship between the radius of sphere and any given one. So here's just a graph of a function that you can see right here. It's not hard to plot it. Basically, it's exponential function. And for exponential function, one way of doing it is just creating table of values and joining consequent points by the smooth curve. We find this point, and then we just draw a line between them, smooth curve like that. In this particular case, radius is the independent variable, and volume is the dependent variable. Basically, what we're doing here, we're creating a table and calculating volume for specific radius. Moving on, what can we show now? Let's say if we take specific volume and we want to evaluate what radius should we use to get that volume, right? So to graph radius in terms of volume, now you can see that y-axis, remember in coordinate axis we have x and y. This graph gives us x as a radius and y as volume, right? If we move to the next graph, it's turned upside down. Now we have volume as the x-axis and radius as y-axis. Opposite, you see? Opposite to what we had before. Considering that, now we have a relationship where radius is the dependent variable and volume becomes the independent one. To graph radius in terms of volume, switch the variables in the table, making radius the dependent variable and volume the independent variable. The red curve shows volume as the independent variable and radius as the dependent variable. Moving on, if we simply ignore the unit and we plot both of these functions next to each other, it's going to look something like that. We're ignoring the units, meaning volume and radius, and plotting both relationship on the same graph. The red curve is reflection of the blue curve in the line y equals x. Y equals x line is such line that crosses between two coordinate axes at a 45-degree angle. That's 45-degree angle. Y equals x. Basically, it's like a mirror for us, and function, the inverse function of volume with respect to radius would be function of radius with respect to volume. And this inverse function is going to be a reflection of our initial function over this y equals x axis. This is reasonable given that the x value and y values were switched on the graph, right? We switched them between each other. If volume was here and radius was here, for second function, we put volume value here and radius value here. The red curve is the inverse relation, and it is also a function. Remember that inverse relation is also a function. You can take inverse relation from any given expression, but not all of the inverse functions are going to be functions. I understand that may be confusing, but remember that one of the basic tests for function is whether there is only one y value with respect to each x value. This is called a slicing method. If you can slice up your function like this, and this blue line passes through the curve only in one point, then this is a function. This is one of the easiest ways of testing whether a relation is function or not. The inverse was found by switching the independent and dependent variable in the table of values. The independent and dependent variable can also be switched in the equation of the relation to determine the equation of the inverse relation. Basically, what they're saying here, that in first example, they switched the values. You see, radius on the left, volume on the right. Now volume on the left, radius on the right. But we also can switch our variables in our equation, and we're going to achieve pretty much the same result. Let's move on to the next example. They're going to show us how it's done. So here, we have to determine the equation of the inverse, but we're going to use algebraic approach. Before we move on, does anybody has any questions about what an inverse function is? The just simple definition of an inverse function? Any questions at all? Guys, please join work with me together. So you don't, Safa, you don't understand what inverse functions, right? Okay. So basically inverse function gives you inverse of the relationship. You understand do you understand what inverse means? So basically inverse means opposite, reversed. Is that more clear now? And if the parent function gives us relationship where volume, this is just as an example, right? In this function, volume of the sphere is defined by the radius of the sphere, right? Imagine if you would like to set relationship in such way that your volume is no longer dependent variable, but independent one. Let's imagine that you're changing your volume and you would like to find what radius it will give you. So if parent function was volume with respect to radius, inverse function would be radius with respect to volume. Is that clear? If no more questions, let's move on. Now, Safa, don't worry. In this example, you're going to understand what an inverse function is. So we have to determine the equation of the inverse. Basically, what we have to do from here we have to express v in terms of r. And to do so, we're going to rearrange our components in this function, right? We have v on the left side, which is volume, r, which is radius on the right side. And we would like to find exactly the opposite. We want to have volume separate from r and r separate from everything else. How can we do that? We're going to use an inverse operations. What inverse operation is? Let's give you an example. You're walking on the street and you walked 5 steps forward. What would be an inverse of that operation, basically? Any ideas, guys? Let's say I walked 5 steps forward. What is the inverse of this? Great stuff, absolutely right. So now let's translate this understanding of basic stuff on algebra. Let's say I add 5 apples. I plus 5 apples or plus 5, right? In Mathematica, there is not always some units behind the numbers. Let's say we add 5 to some number. What would be an inverse of that operation? Plus 5. Inverse would be your answer, guys? Anybody? Minus 5. Great. Same with multiplying and division. You see, on the right-hand side, we have coefficient 4 over 3. It means that we have to start applying inverse operations. First one would be to multiply left and right-hand side by 3, right? Because here we divide by 3, so inverse would be multiplying by 3. Now, on the left side, we have 3 times v. On the right side, we have 3 times this whole expression. It is reasonable that this 3 and this 3 are going to get factorized, right? So we basically canceled this division by 3. We made an inverse operation. Okay, next step, we got this expression, 3v equals 4pr squared, 4pr cubed. What do we do next? We divide by 4p. This is the next coefficient that we have here. And it's not in the denominator, right? Nominator is on top, denominator is on bottom. It's not in the denominator, so we're multiplying by 4p. So now I have to divide by 4p. Simply dividing left and right-hand side by 4p. On the right-hand side, I can factor it out. And what am I left behind with? I'm left behind with r raised to the third power. I'm going to have 3v over 4 pi equals r to the third power. What is the next step? What is the inverse operation of raising number to the power, guys and girls? What would be inverse of raising number to the certain power? Guys, any ideas? You even have a tip on the screen. What is the inverse of raising number to the power? Square root. Great. And not necessarily square root. Roots could have a different degree, right? And if we raise the number to the third power, inverse operation of this would be the root of the third degree, right? So by taking root from the left and right hand side, now on the right hand side, this third power will get factorized with the root operation. And on the left hand side, we got this root of the third power from 3 times v over 4 pi. And that's how we get the inverse relationship. Now the radius is expressed as a function of volume and can be determined for different values of v. Any questions? I think it's pretty clean, pretty obvious. But don't hesitate to ask any questions if you don't understand, because it would be much worse for you to not to understand this in the future than not to understand it now. If you don't understand it now, it's completely normal. But now you can see how algebraically we can get an inverse function. If you will plot this function instead of this function, you're going to get this exact image. Blue one would be the function of v with respect to r, and the red function would be the function of r with respect to v. Basically, what the blue function says to us, it says that the volume grows very fast as the radius increases, right? Volume grows fast with the radius. And the red function tells us that the radius increases slowly as the volume grows. Make sense? So now we're going to answer the question, will an inverse of a function always be a function? Now, looking into this example, we have a function of the second degree. This is polynomial function, or you may know it as parabola, right? Just simple parabola with one vertex. And let's find the inverse function of parabola. And there is another way of finding the inverse relationship. Basically, way of doing it is pretty fairly simple. First of all, you can do this, apply inverse operations, but also you can interchange the variables between each other. Look at this magnificent beauty of mathematics. What we're doing here, we know that the parent function is y equals x squared. It's right here. So we interchange x and y in their relationship just by simply switching them with one another. You see? Now x is on position 1 and y on position 2. And what do we have to do here? Again, we have to express y as a dependent variable from x. Right now, y squared makes no sense. So what we're going to do, we're going to take a square root of this function. Taking the square root gives us plus minus x, right? And here it gives us square root of y to the second degree. And why is it plus minus here? Because x could be any positive number in this case, basically. Because we're taking a square root and we cannot take the square root from negative number. And how can we get a positive number? We can get a positive number by multiplying two negative numbers or two positive numbers. So there are two outcomes here, plus or minus square root of x. And finally, we got our inverse relationship. Plus or minus square root of x equals y. But that's not really good for us right here because this doesn't look like a function. The graph of the inverse relation is a reflection of the original relation in the line y equals x, isn't it? Only non-negative values of x work in the square root function. Only non-negative values of x work in the square root function, right? Because we cannot take a square root from a negative. The square root of a negative number is undefined, since plus minus in the inverse indicates that the output y will include both positive and negative values. So the range will include all the real numbers. So the domain of y equals x squared, the initial function that we covered, is x ER. Basically, x can take any rational number. And the range is x ER, but y greater or equals to 0, right? Y equals x squared is such a function that only positive. The domain of the inverse relationship is x greater or equals to 0, right? X cannot be negative. And the range is y, e, r. Y can take any possible value. Basically, you can see that the domain and range for these two functions are somehow common. But they have inverse relationship, basically. Their domains are also inverse. So the question C, determine if the inverse relation is also a function. How can we do that? The inverse, basically, based on the equation of the inverse relation, each input of x will have two outputs for y. Isn't it first isn't this breaking the first rule about function, that any given input of x should give us specific and only one input of y? Isn't it? That's exactly the definition of a function. And looking in this example, um, each x value would give us two values of y, one positive and one negative. The only exception is x equals 0. And you can see if I apply my slicing method like this, my function has two intersections with this line. It's no good. This function is not a function. The inverse relationship for quadratic function is not a function. Look, I even can have a spotlight. So my conclusion is the inverse relation is not a function, but it can be split in the middle in the two functions, y equals square root of x and y equals negative square root of x, right? Separately, these two functions are totally fine. The inverse relation is useful to solve problems, particularly when you are given a value of the independent variable and need to determine the value of the corresponding independent variable, right? For example, imagine if in previous example with volume, your boss says to you, okay, we need a spherical container for candies. This container should be 3,000 cubic meters. How would you identify what radius should this sphere have? Through the inverse relationship, because inverse relationship basically useful to solve problems when you are given a value of the dependent variable and need to determine the value of the corresponding independent variable. Please take a moment to look through the next example. This is an interesting one. In this case, we're discovering inverse relationship with height, another physical example. Any questions so far, guys and girls? Okay, guys, let's move on. Let's cover this one more example and then we'll make a short break, okay? Archaeologists use models for the relationship between height and footprint length to determine the height of a person based on the length of the bones they discover. Let's make a sketch. Let's say we have a human. Human has a feet. This is more like a hobbit, but not a problem. And we have particular relationship between the height of this person and the size of its foot, right? Okay. So the relationship between height, h of x, remember this is notation for function where h is the dependent variable and x is the independent variable. The relationship expressed in centimeters and footprint length. X is also in centimeters. So this is X, this is H, this is height. And the formula is as follows. 1.1 times X plus 143.6 equals the height. Use this relationship to predict the footprint length for a person who is 170 centimeters tall. So again, example where you are giving with the value of the dependent variable, the height of a person, and we have to predict what the footprint length should be for the person that has a height of 170 centimeters. Let's use this formula. So to predict the footprint length, we have to find the inverse function. We have to express length of the footprint with respect to the height. Now, for sake of simplicity, let's represent h of x as letter y, because it's easier for us to write it that way. Now we have y equals 1.1 times x plus 143.6. Now, as in an example with quadratic function, what we're doing, we're interchanging x and y in their places, right? This is one of possible methods of finding inverse function. Now, we have to express y with respect to x again. To do so, we're going to subtract 143.6 from both sides. Here it is on the left side. And we are going to divide both sides by 1.1. X minus 143.6 divided by 1.1 equals y is now our inverse function. Remember, x, if you see something like this, h or f or any other function to the power -1, it means that this is an inverse of your parent function. It doesn't mean that you raised the function to the power -1. It means that you took the inverse of your function. So now, what we have to do, we have to evaluate our inverse function for height 170. So for basically x, right? Because x is our independent variable in our inverse function. So substituting 170 for x, we're going to see that 170 minus 143.6 divided by 1.1. Going to be 24 centimeters. Person who is 170 centimeters tall may have a footprint length of 24 centimeters. Now to show that it's not just some kind of trick when we interchange x and y values. It's just the way of representing them on the same coordinate axis. Keep y coordinate here and x here and not to change them in their axis as we did in the very first example. But you can do that as well by simply, look, we want to express x from here. So we subtract 143 from left and right, and we divide by 1.1 left and right. And we're going to get exactly the same relationship, but we kept x as the length of the footprint to the right, and h of x as the height to the left. It's going to be h of x minus 143.6 divided by 1.1 equals x. You see, this is exactly what we have here, but with different notation. Now, basically, x is our dependent variable y, and h of x, which was y, now is our dependent variable x. Does it make any sense? Please take a moment to copy this down in your notebooks. And we're gonna start the 15 minutes break and see you at 8:10. Okay, guys? Maybe let's make a 10 minutes break. What would you say? Finish early. Are you with me, guys and girls? Hey guys, I'm back. Is everybody here? Good. Good, Hala. Rana, Safa, are you here? Great. So let's continue. So basically what we covered in this unit, we found a way of finding the inverse relationship. It could be useful in situations where you have to find the inverse relationship of dependent and independent variables. Basically, the inverse function of f of x is denoted by f to the power -1 of x. Function notation can only be used when the inverse is a function, right? Remember that inverse of quadratic function is not a function, but can be split up in two different functions. The graph of the inverse function is reflected in the line y equals x at 45-degree angle like this. Let's review a few methods of finding inverse function. First one is by switching y and x in their location in the initial function, like here. You see, we switch them in places and got the inverse relationship. Or we also can we can perform inverse operations as we did here and as we did in this example, right? If we divide, we multiply. If we multiply, we divide. If we raise to the power, we take a root. That's an example of an inverse operations. Great. Please make a screenshot of this summary. It may be useful. Not all inverse relations are functions. The domain and or range of the original function may need to be restricted to ensure that the inverse of a function is also a function. To find the inverse algebraically, write the function equation using y instead of f of x. Interchange x and y, solve for y. If a, b represents a point on the graph of f of x, and b, a represents the point on the graph of the corresponding inverse function. Get a table of values or a graph of the inverse, Given a table of values or a graph of a function, the independent and dependent variables can be interchanged to get the table of values or a graph of the inverse relation. And finally, the domain of a function is the range of its inverse. The range of a function is the domain of its inverse. You see, that's example where domain and range are interchanging also. So here is your home assignment. From this one, number 6 and number 8 are going to be your home assignment. I'm going to post it after the class today. By the way, did you do the home assignment that was due today? Anybody? Anybody at all? Have you at least started it? Okay, now you have it. You should be able to see it in the Google Classroom. Does anybody have an access to the Google Classroom? Particularly this one. I'm gonna open it right now. I'm gonna share my screen. This Google Classroom. Do you have an access to it? Here. Oh. Oh, okay. This is the wrong one. I see. Weird. Okay, then I gotta take it up. I I don't think we have calculus and vectors right now. But maybe this is the one. I don't know. I'll check it. Okay, thanks for telling me. Let's take a look into piecewise functions. We're also going to have questions about them in their final test. Let's not spend too much time because piecewise functions are not so complicated. So basically, we have to understand, interpret, and graph situations that are described by piecewise functions. What piecewise function is, you're going to see today. So let's see an example where we talk about city parking lot uses the following rules to calculate parking fees. A flat rate of $5 for any moment of time up to and including the first hour. So within the first hour, no matter how long you stay, $5 you pay. Second interval, a flat rate of $12.5 for any amount of time over 1 hour and up to and including 2 hours. So from 1 to 2 hours, you pay $12.5. And the flat rate of $13 plus $3 per hour for each hour after 2 hours. So what we see here, that during the first hour, rate is constant. Let's make a graph of rate or price for parking with respect to time. First hour, constantly $5 I'm paying, right? So it would be just a straight horizontal line. Then from 1 hour to 2 hours, I pay $12.5 no matter how long I stay in this interval. So it was 5 from here, and now basically it jumps to 12.5 as this. You see, basically our function is jumping here. It was $5 before 1 hour mark, right after 1 hour mark, it starts $12.5. But take into account that over 1 hour, so 1 hour is not included here. So it's going to be like dot discontinuity, you see? Empty point here. But here it's a solid point because $5 up to and including 1 hour. Next, after 2 hours, we're going to get a flat rate of $13 plus $3 each hour. So $13 is going to be somewhere here. After 2 hours, we pay $13 plus $2 plus $3 every hour. So 3 hours, we pay 13, then we pay 16, then we pay 18, and so on, right? And now you can see we got this nice staircase. And this is exactly what piecewise function can represent. It represents that in each interval, you have to use your own formula to calculate the result. For an interval from 0 to 1 hour, it's going to be equal to 5. From 1 to 2 hours, it's going to be equal to 12.5. From 2 to 3 hours, and so on, it's going to be equal 13 plus amount of extra hours times 3 per hour, right? So we have basically 3 functions to represent our fee for parking our car. This would be the table of values for our function, and this is how they represent this function in the book. Basically exactly what we get, but you see here they include that every hour it's gradually increasing price. In my example, I assumed that after each hour we're just gonna jump up, but what they say that with each hour your price is gradually increasing by 3. The domain of this piecewise function is x greater or equals to 0, because time cannot be negative. And the function is linear over the domain, but it is discontinuous at x equals 0, you see? Discontinuous at 1, this is the empty point that we sketched before, and discontinued at 2, right here, because we jumped from $12.50 to $13 after 2 hours. So piecewise function is a function defined by using 2 or more rules on 2 or more intervals. As a result, the graph is made up of 2 or more pieces of similar or different functions. That's why it's called piecewise function. Let's take a look into algebraical example to see how do we represent problems using algebraic model and piecewise function. Using part of piecewise function can be described using a specific equation for the interval of the domain. So in example number 2, we have to use an algebraic model to represent the function for parking fees. Exactly what we did here with the table of values. We're going to do the same stuff algebraically. So first case, when price is 0, number of hours is 0, right? Makes sense. If price is $5, it means X or numbers of hours from 0 to 1 hour. Remember, that's what it says in the description, that from 0 to 1 hour, we have a flat fee of $5. Now, next interval, y3 equals 12.5 when x is in an interval between 1 and 2. Now, finally, after the second hour, we have the following relationship for the fee. Y equals 3x plus 13 if we have stayed there for more than 2 hours. And now we can combine all of these relationships into the piecewise notation. Basically, how do we do that? We write our function notation f of x, we say equal to, we make a figure bracket like this, and in this figure bracket, we write all of these functions that we came up with here, 5, 12.5 are also functions, but they're linear functions, right? Straight line, as you can see here. As you can see here, just two straight lines, but they're also functions. We write those functions in the figure brackets, and after the function, we state when it is true. It is true when x equals 0. It is true when x in this interval. It is true when x in this interval, and so on. Basically, we're combining the relations into piecewise function. This is how piecewise function looks like in algebraic notation. The domain of the function is x greater or equals than 0, right? Because these are all values that x could take. X is ours in our scenario, but x could also be some other numbers. The function is discontinuous at x equals 0, x equals 1, x equals 2, because there is a break in the function at each of these points. And there are many breaks in piecewise functions to be found, because basically what's happening here, right after we pass the point of 1 hour, our price increases with a leap. It's like jumping to this value. This is called discontinuity. Now let's practice graphing the piecewise function. And here's a simple example where piecewise function consists of two different functions. We know that function is defined as x squared if x less than 2, and function is defined as 2x plus 3 if x greater or equals to 2. So what can we do here? To plot x squared, we're going to take three values before 2. Or here in this example, they took 5 values. You can take as much as you want, but 3 should be sufficient to plot exponential function. So we take 5 points. Actually, they took 5 points because they want to plot whole parabola. That's wise. So I substitute x equals -2. -2 is less than 2, right? So I calculated by formula x squared. X squared is 4, then -1. X squared is 1, then 0. X squared is 0, then 1. Y x squared again 1, and 2 x squared is 4. This is points for our parabola. And now let's write the points for our linear part of this piecewise function, where it's 2x plus 3, no second degree here, power. So any number that's greater or equals to 2. So we can take 2 as the first number for us. Substituting 2 into this equation would give us 2 times 2 plus 3, which is 4 plus 3, which is 7. And we can see that it really equals to 7 here. Then we have 2 times 3 plus 3 is 9, and 2 times 4 plus 3 is 11, and 2 times 5 plus 3 is 13, and 2 times 6 plus 3 is 15. Now we have tables of values for both pieces of our piecewise function. Using that, you can sketch a graph that's going to look like this. Before x equals 2, we're going to have a parabola. Right after x equals 2, we're going to have a discontinuity, dot discontinuity. This is called dot discontinuity. We have an empty point like this. And after that, we're going to get this linear dependence, as is our second piece of the piecewise function. You see x squared is our parabola here, and this line is our linear dependence to x plus 2. A solid dot is placed at 2, 7, since x equals 2 is included with second piece of our function, right? X greater or equals to 2. But first piece of our function does not include 2. And open dot is placed at 2, 4, since x equals 2 is excluded from f of x equals x squared. Isn't that great? Here's another example, same one, but here we do the opposite. We have to write algebraic representation of the following piecewise function through the graph. And here you can see that it's clearly 1 over x function that looks like this. Also, we can see that as function is greater than 2, we have a linear dependence of y equals 2. So I can write that for 1 over x, if my x value less or equals to 2, and it's going to be 2 if x greater than 2, right? Do you agree with me? I say only greater than 2 because here I can see dot discontinuity. So 2 is not included in the domain for linear function. Here you can see the answer for this problem. The graph is made up of two pieces. One piece is part of the reciprocal function defined by y equals 1 over x when x less or equals to 2. And the other piece is a horizontal line defined by y equals 2 when x greater than 2. The solid dot indicates that point 2 and 1 over 2 belongs with the reciprocal function. Any questions about this? Okay, then great. We can skip this example and go ahead to the summary. Some functions are represented by two or more pieces. These functions are called piecewise functions. Each piece of the piecewise function is defined for a specific interval in the domain of the function. That's important. Here, this function is defined as 1 over x for domain for x less or equals to 2, and as 2 for x greater than 2. This is an example of how it's defined in the domain. To graph the piecewise function, graph each piece of the function over the given interval. A piecewise function can be either continuous or not. If all the pieces of the function join together at the endpoints of the given intervals, then the function is continuous. Otherwise, it is discontinuous at these values of the domain.